So hello again. Are there any questions? Well, okay, as I can't see any questions, we will start a new topic, which is the finite difference time domain method. First, I would start with a piece of mathematics. The equations of electromagnetic field have been first written by James Clerk Maxwell as quaternions, but later have been written by Heaviside in a manner that we already know, and that's a set of partial differential equations. Equations containing derivatives against time and space variables. And now those equations are difficult to solve, at least in general conditions, general boundary conditions. There is not a known solution which would be algebraic. That's only a solution that for simple cases in closed form, but we have to find numerical methods to solve it in other cases. Now, the problem of solving differential equations is very old. The first known method, as far as I know, has been introduced by Euler. And Euler's method for solving a differential equation is quite simple. Let us have a function y which we want to know, but unfortunately we do not know the function itself. We only know, at some cost, its derivative. So we know only the derivative against x, for example, of the function, which is f. And we, of course, have to know a condition, an initial condition. So we know that epsilon without derivative in the point 0 is a. Now this is pictured in a graph. So we have x, we have y, and at the beginning of the calculation we know that y must be equivalent to a. But we do not know anything else except for the derivative. What a derivative of a function is? Well, it tells us how fast is the growth of the function. So let's make a first assumption that the function f is continuous and that it could change, so there are also higher derivatives of epsilon, but changes only slowly. If that is the true, what we can do is to make an estimate of the function y for some larger x. So for example, over here, we make an estimate. How we make it? Well, okay, we say we know the value here and it should change with the speed given by the function. So we now know that the rate of change tells us this. So let's say, okay, if the step is small, the next value of epsilon would be this. And then we return to calculation, get the value of the derivative, and make another step. Possibly, for example, that the f here has a different value, so we will have this step, and in the next step, I have not more space but for 3 steps. For example, it would run this way. So we have estimated the function by 3 line sections which have been always equivalent or calculated out of the first derivative at the starting point of the section. And we have an estimation of the function value over here. Now this is very nice, but you possibly would agree that as the derivative changed, it seems that it not only changed just here, but it changed along the way, so that possibly the real behavior of the function was something like this. So we have here an error, a numerical error. The method produced a solution, and that solution was not exact, but that was an estimate of the solution. Well, what can we do to improve the precision of the solution? The first thing would be that we make shorter steps. With shorter steps, we can get a better solution. So, for example, we make half the original step, and instead of getting over here, we would then again have a set of straight lines, but this one would resemble the original function much better. Now we would guess we could get shorter and shorter steps and get better and better solutions. That would be the case if we had an infinite precision in our calculations, but unfortunately for reality this does not work very much. Then after this simplest method of Euler, there have been a number of new methods getting estimates which estimated, for example, in that way that they calculate both the value of the derivative here and here and make an average for the step. Even the derivative could be taken in several points, and most of that method has been introduced by Runge-Kutta, and there is a number of Runge-Kutta stepping algorithms which have better and better precision on the expense of more complicated calculation. Just I would like to know that there is one trick that would change the Euler method to be much more precise, and that is the case when I will start a new run here. We can get the direction by the first derivative here, but we know that the direction here is a bit different. What if we have used the derivative just in the middle of the interval? Well, then we would have much better estimate of the solution, and in fact this would cover also the next derivative of the function. So if the function was quadratic, we would be completely correct. Only higher terms in the series of the function would then cause problems, and moreover, with decreasing the step, we would have quite a fine solution. Unfortunately, the problem is that that would cost us a calculation of the function in the middle of the interval. Now, that might not be possible. In some cases, we do not know the derivative at any point. We only have some points at which we can achieve the value of the function f. And that is a problem. So that's the first point, but fortunately I will show you an algorithm which can only get the derivatives of the function just in the middle of the interval. It cannot get it here, but for electromagnetic field it can get it just in the middle of the stepping interval. So we will get a lot of precision with a very good idea that has been introduced some in 60s of the last century. But before we get there, I would like to start with another look on this electromagnetic problem. You possibly know that, let's say, in the time of big French Revolution, Great French Revolution, there have been excellent physicists and the physics more or less matured. There have been just a few minor problems like the behavior of gas at very high pressures or very low temperatures, or the behavior of materials close to absolute zero. The rest has been solved and everything worked. And everything has been, after all, described by ordinary equations or differential equations. And the point was that the physics and the philosophers thought that we have a chance, knowing all the laws of nature, we have a chance to do two things. First, to measure current status of the nature, and by applying the law we could prolong it to the future. So some people really thought that they will be able to find out the name of the next president if they knew exactly the situation, if they measured something exactly and then applied the law of nature. That was the mechanism. Some people thought that mechanics could predict the future, but also find the past. So that was a very nice idea. Unfortunately, then came a person who made this a problem. And the problem was the quantum mechanics and the uncertainty that it has been shown that you can't measure anything absolutely precisely, or more or less you can not measure both the position and the velocity or momentum of a particle. That if you measure one of those parameters exactly, absolutely precisely, you know nothing about the other. So the problem was that this approach would be possible, but you would have to guess the initial state, and that's impossible. But for a case which is a model, which would be Maxwell equations fully describing, that is electromagnetic field in a volume where at the beginning of the experiment there is no field, well, then we know the field exactly because we know that the field is zero. And we know exactly the law of evolution, which is Maxwell equation. Then we could describe the evolution of the field in that volume if we just insert a perfectly known field or impulse into it. Now, in order to do that, we will first examine Maxwell equations and find out how to solve them into or how to change them into an equation which is describing an evolution of a system. So we have a Maxwell equation, for example, now just in the first row I would use the notation with arrows. This is a vector and this is a vector, and some of you would know this equation, this notation. Others possibly have written it in a way of rotation E or circulation, which in coordinate system could be described by a vector product of nabla operator and the E vector anyway. But let us do that in Cartesian coordinates to find out what this equation means, really. So the nabla operator, the vector product here, could be described by x0, this unity vector in the direction of x, y0, the unity vector in direction of y, and z0, the unity vector in direction of z. Now, the second row would be those partial derivatives inside the nabla operator. So we would have the first derivative against x, the first derivative against y, and the first derivative against z. Well, and the third row is the vector E, so it's E, x, E, y, and E, z. And in order to get this, yes, this is to make the complete equation. So we have there a vector which is minus derivative of b x against time minus derivative of b y against time and minus derivative of b z against time, and this is a vector. So this symbolic notation looks in Cartesian coordinates like this. And now let us find, for example, the first equation, which would be for Bx, the x component of the flux density of magnetic field. So in order to write this equation for the time derivative of Bx, we would have to calculate the first part of the determinant here. So we would hide those two parts, the row and the column, and we'll get an equation which reads, so the minus derivative of Bx against time is equivalent to space derivative of Ez, the Z component of the electric strength, against Y, minus the derivative of Ey component against Z. So this is one of the equations we have obtained here. We can of course get a set of three equations out of this notation. I will just first comment on this. So we have an equation that gives us a time behavior of magnetic flux density depending on the change, or let's say space derivatives of electric field components Ez and Ey. So switching back to the Euler's method, we are able to get the time derivative of the function if we know the distribution of Ez and Ey. So if we want to make an estimate of the next value of the Bx, I will call it next, then we have bx, I mean the current bx, I will not write it, otherwise I would run out of the paper, but to get the next value I use the current value and I add some time step, delta t, times the time derivative of bx. So in order to get the time derivative of bx, we understand that minus the derivative is this. So if we interchange those two terms, we have plus dbx to dt. So we can write it like this is a simple result of the Maxwell equation. So the Maxwell equation is a kind of evolutionary description of the field. We can find out the time derivatives of the fields, and therefore we can estimate the value at some next time. So we can find out the next value of magnetic flux density based on the electric strength, based on a known distribution of electric strength. Now we would need different derivatives here for different components of B, X, Y, Z. But anyway, we will get three equations that can get us to a solution in the next time step. But this equation contains functions. Those are continuous functions in this equation, which is not the case what we get in a case of discretization. In fact, if we apply discretization onto B or H, E and D,